Good afternoon, my name is Yamagata from Cooking, and we're going to present problem number 7, three-sided dashes. First, a quick overview on the last small introduction, then passing to the three theoretical models that we did, then the experimental set of used, our results, and the conclusion for this problem. The problem statement says that symmetrical moving type is often associated with the idea of order of permanence. What should be the physical and geometrical characteristics of a cylindrical dice so that it has the same probability to end on the side and on one of the spaces? First, we ask ourselves, what makes dice fair? We took some commercial common dice and we observed that they have normally equally distributed mass, they are symmetrical, all their faces are plane, and all their faces are equal. However, as cylindrical dice, where we define the cylinder as a solid geometrical figure with straight parallel sides and a circular or oval cross-section, have two equal plane faces, but one cylindrical face, which we will be calling side or sides. And it's pretty clear to see how this doesn't really match up to some of the characteristics we have for the most common dice there are. Now, we have a hypothesis for the cylinder, that is that there will be a specific radius-to-height ratio that makes a regular cylindrical dice fair. Now, we took from articles about probability in solid causing that practically any finite uncertainty in the initial conditions can lead to the uncertainty of the resultant tossing. Like this, we confirmed that the tossing of the coin is pretty much random. So, for the main part of the experiment, we didn't really control the tossing, though it's for some part, and I will explain later. Now, we did some assumptions for our main theoretical model. That is that the dice would be a regular cylinder, which means it has two equal circular, not oval or linear shaped faces, and the sides are perpendicular to the faces. So, yeah, it also has a regularly distributed mass, and the initial conditions would be random because of the last slide. Now, in the theoretical model, we have some variables that first are R, that is the radius of the cylinder, H, capital H, that is the height of the cylinder, and then lowercase h, which is the one I will be using the most. That means pretty much just height divided by 2, so the height from the center to the top, if that is understandable. Now, we use P sub s to represent the probability of the dice landing on the side, and alpha as a coefficient that represents the lowercase h divided by the radius, and for other graphs, we will be graphing alpha as the x-axis and the probability as the y-axis. Our first model is about surface area of the dice, which is basically, all of these models are taken from what we believe were the most common they were the most common ones used in literature, so that's where we kind of moved from. First, this one says that the probability of the dice landing on one of its faces would be proportional to the surface area it has in reference to the surface area of the whole dice. So if the surface area of the side is the perimeter of the circle times the full height would be 4 pi times radius times the small height, and the total surface area would be that plus 2 times the area of the plane faces or the area of the circle using r as a radius. Now the probability would be the surface area of the sides, we're using the probability of the landing on the sides again, divided by the surface area of the whole dice, and then we start solving this equation to get to 2h divided by r plus 2h, and this would be equivalent of using the alpha coefficient we mentioned in the variables to this that is right here. And there is the graph. The equal probability should be reached at 0.25. We define the second model as 2 yards, and it's pretty similar. It practically says that the probability of the dice landing on each one of its faces is equal to the proportion of the angle or angles that's within the side of the water cylinder divided by the whole circumference, which would be 2 pi radians. That is because when it lands, the arc of the circumference that circumscribed kind of touches the surface in a certain point, and that defines where the dice will bring on. So we use trigonometry to find what the probability of that would be using the variables we have and we know. And we just solve those equations, and we get that the probability would be 2 beta, because beta is the angles, that angle over there being beta, I'm sorry. So it would be 2 beta because there are two angles that sides, of course, since it's a phase above and a phase below in the sides, and divided by 2 pi. Substituting that with what we have in terms of alpha, it would be twice the inverse tangent of alpha divided by pi. There is a graph, and the equal probability should be reached at an alpha of 1 divided by square root of 8. Now, for the 3D model, it's pretty much the same as the 3D model, except that in this one, we're not basing ourselves in the circumference that subtends the 3D plane of the dice, but instead we're using a sphere that would simply describe the cylinder. We use this formula to find the solid angle that subtends one of the plane faces, and though we don't have a formula for the sides, we know that there are 2 plane faces, and the solid angle should be a total of the sphere. So to find the solid angle of the sides, we just take the solid angle of the whole sphere, which would be 4 pi is the radius, and subtract from it twice the solid angle of the plane faces. And we reach 4 pi times alpha divided by alpha squared square root of alpha squared. And now the probability should be that of the solid angle of the sides divided by 4 pi, which is the radians in the sphere, and substituting in terms of alpha, and we get to this. And the graph, the equal probability should be reached at an alpha of 1 divided by square root of 3. And here are all the 3 models in the same graph, and that gray line represents the equal probability, so it crosses 1/3 in the y-axis. Now, for our experiment, we 3D printed 6 dice, all with the same radius of 1.5 centimeters, but all of them with different heights. They're not exact because, well, the 3D printer is not exact for infinite decimals, but we try to get it as exact as we could, with heights as we see in that side of the table, which will represent the alpha coefficients of 0.25 and all of that in that column. And as you see, those represent the surface area model, the solid angles model, and the 2DR model, adding 3 additional heights to have more information. We also tried with some twin dice that are a little bit less exact than the 3D printed ones, of course, but they also notice this is something. And in this one, we use 2 sets. One of them have an alpha coefficient of 0.5, and the lower ones have an alpha coefficient of approximately 1 divided by square root of 8. Now, we draw, they also have 3 each, so it's radius 2, 3, and 4 centimeters, respectively. The ones with radius 2 and 3 were dropped from a half a meter height, and the 4 centimeter ones were dropped from a meter height. These ones, we only drop them, always with the blue side face up, and we toss them 600 times. The 3D printed ones, however, we just stop them, toss them upwards without really regulating any conditions, and we toss these ones 150 times each. So our results for the experimental part with the 3D printed dice is in this graph. The x's are the experimental results. And for the probability, we just did the amount of times it landed on sides and divided it by the amount of times we tested total, so 150. And there is graph with a margin error that was calculated with a formula for probability margin error. So as you see, they don't really fit any of the theoretical models we had. However, since we follow the tendency that, well, it curves upward, and as the alpha coefficient goes up, the probability for the dice to land on its sides start going up as well. And it is pretty interesting also that even though it's not shoulder, because I couldn't put the line here, the x experimental x, the lower one, is pretty close to 0 in the y-axis. So if we were to move the curves a little bit more to my left, it would fit much more approximately the curve that we have in the theoretical model. And now here are, oh yes, very interestingly, the experimental probabilities were equal in the dice that had high equal radius, which goes against all of the models that we found, but that's just what the experiment gave us. Here are the same graphs, but instead of graphing the probability for the sides, we have the probability for each one of these phases, and we see there are 2 crosses on each part. So it's because it wasn't the exact same probability for both phases, but they were pretty close to each other. Now with the wooden dice, since we always drop them with the blue face facing upwards, most of the time they had they had a bias to win with the blue side facing up again. However, even though the blue probabilities are much higher than they should, or higher compared to the second phase, the ratio between the second phase and side remain pretty much the same. As you can see in this chart, where we have the ratio between the second plane phase, and the sides. The coefficient is pretty much the same. So even though there was a bias towards the phase that was facing upwards when we dropped them, they remain being proportional. Now, as a conclusion, our hypothesis was confirmed, and there is a specific height to radius ratio for a regular cylinder, which is of a third, because also if we see here again, the one that had a null coefficient of 0.5, which is highly equal radius, has pretty much the same probability on each one of these phases, to confirm just what we did with the 3D printed dice. Now, the random results require minimal initial height, as the ones that we tossed with the blue face facing upwards had a bias towards the side. They had to be tossed from a higher height to make it spin more linear in another random phase. And there may be a minimum height to radius ratio below which the probabilities for size is only consistent, as we can see with the graphs being very close to 0. The theoretical models don't fit the experimental results perfectly, so they do show us an approximation, and this could help us predict the probabilities we will need for an irregular shaped dice or another cylinder. Here are my sources. Thank you for your attention.
But then you said drop height.
Oh.
your responsibility to make sure that everybody can hear. You've got 3 microphones there. So to be thinking about how you want to just test that.
Hi. Might be a little bit loud. Is it too loud? Yeah.
But anyway, you have to manage that so we can hear, and maybe you give that to her or something.
All right.
During the fight. And I just remind people that you're not allowed to be using internet while we're doing this. Okay, so please continue.
So today I'll be presenting 3-sided dice.
Sorry.
So here's the.
We can see the clock. They can see the clock. You can or not?
No, when you're up here, we cannot see the clock.
Can the clock go to this one? You just have to have your teammates, don't you?
Yes.
Okay. Get your teammates to go 12 minutes to go, please. So teammates have them. Okay. Do you want to start again? See if you can have your arm back.
That's what the clock is saying.
Yeah, off we go. So, you know your points now.
Okay. So today I'll be presenting 3-sided dice. So here's the overview of the presentation. The pros are that the reporter introduced the fair conditions of different commercial dice. She also did deliberately control the tossing, which shows which was an experimental way to prove her theory of complete randomness. The cons are, first, that she assumed complete randomness, which contradicted her later statement of drop height and many other factors I'll discuss later. And she also didn't show the way of tossing, which cannot be show the toss is random. So for the geometrical theory part of her presentation, there are clear definitions of the geometry of the dice. The theory is relatively easy to understand, and she compared 3 different theoretical models. But the cons are that she uses areas that don't consider bouncing or tilting of the dice. There are no physical properties involved, such as the coefficient of restitution, friction with the surface, angular momentum being part of the dice, the linear velocity of the dice, which can then change into angular momentum. And having 3 theories do not make sense. It would make sense if one of them explicitly matches the data, but having 3 with none of them matching doesn't really make sense. She also didn't specify a specific drop height for randomness. She mentioned she tested 2 different drop heights, but she didn't give a barrier for which it's, say, like 99 or 99.5% random. She also incorrectly assumes that mass doesn't matter because it will affect the angular momentum of the dice, and that will be covered later. So for the experiments, she used a sufficient amount of dice sizes for the experiment, and she also controlled the ratio with 3D printing. Some cons are that she couldn't verify or know how the 3D printed dice was made, so even if it were asymmetric and she were still using a symmetric model, she wouldn't be able to compare or even use that for error. She has no explanation for deviation. Her data points are unlabeled, and she doesn't explain the difference between the wooden dice and the cylindrical dice. I mean, the wooden dice and the 3D printed dice. Although when I asked the reporter, she did seem to concede that the coefficients of restitution may be the same. She assumed different probabilities for 2 faces. She couldn't control the mass distribution because of hollowness. She didn't experiment with different initial conditions. She seemed to drop from 2 different heights for 2 different materials, which I think that has too many free parameters to be able to make scientific conclusions. And there's little data around areas with high slopes of the theory, because I can't see that. Because areas of high slopes will have more error if you have data points there. So I would like to discuss first the geometric theory. I'd like to talk about the possibility of using a bounce model, and also how you can compare these models properly for a more proper presentation. You can also like to discuss really important things, which is probability manipulation, because unfortunately, so far the reporter only the problem statement asks for the physical and geometrical characteristics of a cylindrical die, but I think the report only mentioned the geometrical characteristics, which unfortunately omits all the physical characteristics which can be achieved through changing the initial conditions. So the probability manipulation includes angular momentum, linear velocity, and friction, which changes all of them. And I can see the clock by the way. And you can maximize randomness by increasing the drop height, like the reporter said, or by changing the coefficient make a limit such that a geometrically unfair dice, as it approaches that limit, becomes more fair. That concludes my presentation. I can begin the discussion. Okay, so thank you. I meant. Could I please have a pen? Okay. So you mentioned you used 3 different models.
Yes.
And actually, I read this paper that used those 3 exact models for comparison. And yeah, like your theory shows, it really matters. So I'd like to propose another way to approach the problem. So did you consider analyzing the bounces of each? Okay, so first of all, we can approach this in a more 2-dimensional fashion. So let's say a dice contacts the ground like this. Did you consider this configuration, if it touches the ground statically, do you think you could use this situation to model a geometric probability based on a static model?
Can you repeat that part, like the static model?
Yeah, sorry. So assume you have a floor over here. Actually, so let's say you have a dice like this and you have a table. So let's just say you let it go at rest. And there's any random angle, you just put it there, right? So this is actually a pretty easy way to geometrically randomize the angle, put it down, what's the probability that lands on its edge or on its head. So do you think there's one way of, do you think that could be a valid model?
In some way, yes, because, well, if you were to have a dice with a very big side with very small faces, then of course there's a probability you're just rolling in your hand and put it down, that it will land on the face that is bigger. So yeah, it's similar to the surface area I mentioned.
Right, also, but that's actually incorrect because if you just let it go like this, that's not how really dice movement works. It's opposite. So another way you could.
Do you mean in respect to the angle? Like if you look at angle?
Yeah, this one is complete angle randomness. So if you drop it from the air, it's going to be different, right? It's going to start with some initial energy, and this energy is going to be some, say, gamma and word gamma is some energy decay constant. So one thing cool about this model is that using energy, you can pretty efficiently model this system because let's say you have a dice that's like currently like this and it wants to go like this, right? This is an edge fall and this is a head fall. Let's just say this is a head. To change from this position to this position, it needs to reach a state where where its diagonal is perpendicular to the floor, where the energy is the highest. And by using energy decay, you can basically sum up all the probabilities of it landing in an edge-induced fall position, multiplying by the probability that it doesn't escape. And it won't escape anymore if its energy is less than, it is less after a couple of bounces.
Okay, so if I don't understand right. So what you're saying, when it lands like this, it would have this surface here in the moment it touches the floor. So yes, depending on where respect to the perpendicular line the gravity center is, that will pretty much define the phase it lands on, even though of course with the energy it would affect. But yes, I did mention that the center of mass affects the side it lands on.
Sure. Okay, so that's basically my suggestion for improvement for the geometrical theory parts. Now I'd like to talk about comparing different initial conditions. So you mentioned earlier that you don't think initial conditions are important for this test, right?
Well, yes. What I'm saying is more that even though initial conditions determine the final landing, the initial conditions would have to be so perfectly controlled that they are pretty much not possible.
So it's very sensitive to its initial conditions. So it's almost chaotic. Okay, sure. First of all, chaos is when sensitivity grows exponentially across time, which doesn't really happen over here, but that's all right. So I'd like to introduce angular momentum, right? Because if you Yeah. So if you have your dice like this and you give it some, you roll it, you give it some angular momentum. The dice is going to want to conserve its what? Could you please go to a drop height experiment, please?
Yes.
Yeah, okay. So as I was mentioning, so if you're like a casino dealer and you give this dice some initial angular momentum, because of the conservation of angular momentum, even if you have slight deviations in its initial conditions, it's going to want to conserve that angular momentum. So let's say if you just drop it like this, it lands on its head. But if you give it a lot of angular momentum, it's going to want to land on its side because of those are called physical conditions.
Okay, yes, but there will be physical conditions, of course, that you have to control to have a certain angular momentum. And by hand, that would be very hard to control. You can just control the exact force, you give it the exact angle, you drop it at the exact conditions of here. Things that could affect the way the dice and the when it falls.
Actually, no. It's actually pretty well known that, at least for a fair geometrically fair dice, if you drop it at rest like this versus if you just give it a gentle pull with your hand like this, the probability of it landing on its edge doubles. It doubles. So it's actually pretty hard to control using angular momentum.
Okay, that's what I said. You can control the angular momentum.
Oh, so did you control angular momentum?
No, we didn't.
So how did you drop the dice?
For the 3D printed ones, we tested randomly, so we just shake it in the hands and drop it like when you're playing with dice. And for these ones, we hold them up as straight as we can get them at the heights we mentioned in this slide and just let them fall.
Oh, okay. So which orientation did you hold them? Head up.
Always with the face one up, yes.
So is holding it with so how high did you drop the dice from again?
The first two, the smaller ones, we dropped them from half a meter from the surface they were going to land. And as we saw that there was bias, just the side that was mixing up, the biggest dice, the one with the 4 centimeter radius, was dropped from a meter high from the surface.
Okay, I see. So you basically concluded that the higher you drop the dice, the more random it was.
Yes.
Yeah, I agree with that because the more collisions it has with the ground, basically it has more times to. It basically just becomes more random the more collisions you have. So if you just drop it from this height, it's much easier to control than if you drop it from here. But again, there are other ways still to increase the dice. For example, you could give it a large linear velocity by tossing it forward, and it can, through friction with the surface, linear velocity can transform into angular velocity. So if you hand it with no angular velocity moving like this, and you go woo, it's going to start spinning and giving it an angular velocity, and through conservation, it's going to stay the same. So you also mentioned you tested 2 different wooden dice and a 3D printed
Yes,
dice.
we did.
Okay, so as I asked in the question component, I still don't quite understand why you tested 2 different dice if you assumed they were the same.
Oh, well, first of all, we see that the change of material doesn't matter because some parts of the probability stay the same, like the ratio between the 2 places that were not biased. And for the ones that have the probabilities being as regular as we could, like with no bias, they still were similar to the 3D printed models. And that's pretty much the main reason.
Okay. Also, for your model, you assume that, because you didn't use this bounce model obviously concerns coefficient of restitution because you have energy decay until it comes to rest at a certain position. But do you think coefficient of restitution, how far it bounces up and down, I can see the time, will change the probabilities?
Of course, because the more it bounces, it's like it were being tossed again and again and again, so it would sound like a different place. But as we were doing it to test it as random as we could, like shaking it and throwing it, we considered that it wasn't that important because it was still being as random as we could get.
Okay, could you please turn to page 22? so I also noticed on page 22 that your deviations are really, really large. So could you give a brief explanation of that?
I'm afraid we're out of time for that. Thank you very much. Well done. And we move on to the next one where the proponent summarizes the discussion. So you have 1 minute to summarize your discussion, Alex.
Okay, thank you. So I think the reporter and I had a very insightful discussion. First, I introduced to the reporter a bounce model method. I think more is known to new experimentation and various literature to more accurately describe the dice. I also talked with the reporter about examining the other half of the three-sided die problem, which was changing the physical conditions, the initial conditions of the dice, and how by changing some conditions, such as by making the dice more heavy or by making it more light or changing the angular momentum, which changes the angular momentum, you could increase or decrease randomness. For experimental control, I clarified the tossing method. The reporter had two different tossing methods, one at rest and one that's like playing at a casino. And we also saw that the higher you drop the dice, the more random it will become. And obviously for the physical conditions, that will also change as well. Like what the reporter said on page 24, the probability is actually sensitive to initial conditions and the error will grow larger during the higher slopes. Thank you.
Thank you very much. Well done. So now we move on to questions of the reviewer, to the reporter and the author.
Okay, so how many times did you toss the dice?
The 3D printed ones, 150 times each, and the wooden dice, 600 times each.
For your 3D model, it assumes the sphere, right? That the 3D sphere model
Yes.
assumes that the coin is equally likely to turn on each side, correct?
That the arc of the sphere that it lands on would determine the phase that it lands on.
Yes, but the probability is limited to a sphere, right?
Yes.
Okay. Could you turn back your presentation, please? I can ask one question while you open your presentation. Do you think that the conjugate is uniform that you used?
Not exactly, but it's not as non-uniform to affect the experiment.
Okay, and the friction wasn't measured or considered experimentally?
No, it wasn't.
Okay.
Let's like to do ASCO.
Slide, with the results, I did not, I think slide 25, I think. 25, yes. And those are the only two coefficients used, DHD ratios.
Yes, or wooden dice, yes.
So, two ratios.
Yes, it's considered only those dice where we control the initial conditions.
And are those theoretical ratios?
No, these are the experimental ratios we got.
But are they based on theory or only your condition configurations?
Well, the ratios, as I showed in the slide,
No, but those specific two ratios, are they by 3D static theory or?
they are not solid angle model and the height equal to radius.
Okay. Thank you. And the second slide, please. Can you go back? How did you control the the small variations that were stated could still show in statistically same probabilities. The opponents said that the math distribution cannot be controlled in this section, but we think that the 3D printing is a good way to control this, but not to put the dice that were used. For the discussion, there were three main points in the discussion. The first one was the drop randomness. The opponent suggested that the fact of large initial energy and drop probability, but the reporter did not provide a clear understanding or a conclusive answer to that. And we agree with the opponent that energy does, in fact, produce the differences in bouncing, which then affect the probability. For the angular momentum conservation, the opponent suggested that the current method largely affects the probability, such as that the free fall will land on the side that is downward facing, or that horizontally tossed will land on the horizontally tossed side. We agree with the opponent, which this is of huge relevance to actual probability. They also discussed the COR, but the presenter did not really understand the question, so we agree with the opponent that this is important. Well, so for the final verdict, we think that there is no optimization in this experiment. There is sufficient number of physical parameters that are none, and the opportunity time. Sorry.
And so that make it quite simple time. So thank you very much. We now move on to the next stage, which is the final concluding remarks of the reporter for 2 minutes.
First of all, I want to say that I consider that the opponent mentioned some really good aspects that weren't in the presentation. However, in the way that we control the experiments, they were really part of our mission. He mentioned a lot of different ways of tossing and how they would affect the physical conditions of the randomness. However, as I mentioned at the beginning, even though, and again, as I said in this discussion, the initial conditions do affect the tossing. They have really sensible parameters, so even though you can control the initial way of controlling it, the randomness will still be there because you can fully control every single parameter that there is in random tossing. We try to test them as randomly as we could. We try to use materials that were regular, and even though they were not perfectly regular, we kept them having matching probabilities for the models we tried. We did a lot of experimentation with the hydrogen ratios, thus getting to the conclusion that that is the important part to achieve regular cylindrical dice to be fair, as we showed in our slides. With the dice, even though they had different initial conditions, different materials, different sizes overall, they still had matching results for the final conditions. As you can see, with the dice with the alpha coefficient of 0.5, which is height over radius, being the equal probability one, and even for the one that was with an alpha of 1 divided by square root of 8, we didn't exactly have the same results, but the two phases that were unbiased because of the initial height condition, they still had the same proportion. So yes, the height to radius ratios is what determines the firmness of the cylindrical dice, and that is achieved at a height over radius. Thank you.
so my grade is 4. Arian is 4. Nina, 4. Stanislav, 3. And Marina, 2. Well, there. The opponents from Chinese Taipei, I gave it a 6. We have an 8. From Dina, it's an 8. What? 8. Stanislav, 7. And Marina, 7. Well done, guys. And the last one was review from Croatia. I gave it an 8. And Marian, 7. Tina, 5. Stanislav, 6. And Farida, 3. Well done, team. Okay, so we can give you a little bit of feedback now. We don't want to spend too long on this, but yeah, so Farida, you obviously did not take much of the presentation, just yet so. What was your breakdown of the marks?
So I will first tell you the distribution of marks. I will select part I gave them marks 75, and the discussion with the opponent I gave them 5. Because the residency effective, and seeing that opponent is going to perform the experiment very well, and she did the things professionally. And that's why I give marks to her, because there is, as mentioned by the opponent, that is experiment. So I will discuss in the section first.
And the previous game 4. Do you guys need us to use microphone for this? Would that
It will be better.
Yeah, do you want us to get that? The acoustics in this room are not great, so you definitely have to find. For Canada observing, this is a great chance for you to watch and learn.
Hi.
You're going to get a chat show host sometime, aren't you? If you just see it, this is the beginning of your career. Okay, the two, one of you two like to talk about the 4. So you guys have time off, but was there anything
4.
that wasn't mentioned by Karina?
Sorry, for report. I was 1.5 in the explanation of phenomena and model theory. I was not too much relevant experiment. I don't see that. And in discussion with opponent for me was 1.25, and in total I was almost 4.
Okay, and so now moving on to the opposition. Dina, you gave that an 8. You want to talk about that? Yes.
For the opposition, I really enjoyed because it was not your job to do the experiment by yourself, but you showed the initial condition and for tossing the dice, and also the mass distribution is very important, and also to find it not only by the experiment, by the simulation. We can show how this task is working, as if the probability of landing on the side, is it carefully has been built or not. It was really good, and so in some details I gave you 1.15 and 3 and 3, totally 8.
Yeah, I gave you those great there, which was a 6. And my concern all the time was that you were straying into presenting what you've done.
And that's, of course, you have to talk about what they've done. And I was saying, how far is he going to go before I have to say, excuse me, you can't say that. And so I was always thinking, is he really talking about her work, or has he got this idea of what my answer is? And so that's difficult. So the data, I thought there was one point where there was data, and she worked out ratios to 5 significant figures from, I don't know how many throws, but I thought that was just, some things in the report you could have picked up on. So my breakdown was, so 1.5 questions, quite a good report, but then you got down on the discussion, just gave 1.3 for the discussion part on that. Okay, and on to the review. I really like review, and I was highest on that one as well. It was awesome, and yeah, and if you hadn't, you would have had a 9, but you only asked questions really of the reporter, and we have to look at a suitable time allocated to the reporter and the opposer. And then also you didn't pick up on the significant figures, so which just shouldn't have been here. So, but I really enjoyed it. I thought it was a great summary, and I enjoyed listening to you. Well, presented up for reader, get to the 3.
Yes.
Did you see that?
The report is very weak, both mathematically and the experiment is not performed in a controlled environment. Neither they consider the surface on which the dice they drop, and what is the configuration of the surface is a very important question, which is also raised by the reporter. So reviewer doesn't pay the attention on these things. The reporter only mentions those things which is already described by opponent, discussed by the opponent, and they doesn't bring any new furthermore thing which can be asked, but they did not pay attention on that. So both experimentally and theory on the theory side. So if the report is very weak, then there is a lot of room for the opponent that they can ask opponent and the reviewer that they can perform their job. So I think they didn't perform their job rightly, so that's why I gave it 7.3. It's a superficial part. As if you see, so my partial rating is because if I mark them, everything was superficial, not deep understanding of. So I gave 0.5. Question they asked, they asked only 3 questions, and then the 0.5 for the review, report on review, and 0.5 on the opposition, report, review on opposition, and discussion analysis is almost not present there, so that's why I give that 3 marks.
So thank you very much, everybody. We don't want to be too long and turn it around, so come